Hi, my name is Paris, and this is Lab 5 Magnetic Braking with Faraday, and this is for Physics 2212. Just a quick introduction to this lab. The purpose was to collect observational data of a magnet falling through the tube of aluminum foil to create a computational model of this magnet-tube interaction, and then to compare the computational predictions with the observed data. The following are the materials that were used in this lab. You have a smartphone, a bar magnet, a roll of aluminum foil, and a ruler. Note that it is critical to only use a non-magnetic metal for this, as the magnet would be attracted to a magnetic tube and the experiment would not work. I will cover the physical part of the experiment first, and then I will go over the computational model. The experiment done in part 1 was the physical portion of this lab. We dropped the magnet down the aluminum foil tube as shown. From the video, we can see that the magnet moves slowly through the tube. This is because the induced electric field from the magnet and tube interaction opposes the direction of the falling magnet. As the magnet falls down the tube, it becomes oriented sideways with the north and south poles now positioned horizontally. In free space, the magnet's acceleration downward would be only due to gravity, as it would not be affected by an electric field. After dropping the magnet down the tube 5 times, the average time it took the magnet to fall through completely was 2.002 seconds. This time will be important for the next part of the lab. In part 2 of the experiment, a computational model is made using GlowScript. Figure 1 shows a computational model of the magnet and tube as the magnet is falling through the tube. The blue part of the computational model shows the counterclockwise current, while the red shows the clockwise current. Figure 2, we see the computational model of the magnet and tube at the time when the magnet has exited the tube, also shown as a velocity versus time graph for the magnet. And in this velocity versus time graph, I have marked certain key parts of the process. In part A, the magnet enters the tube. In part B, the pole orientation changes as the magnet is falling. In part C, the magnet is positioned horizontally. In part D, the magnet is falling through the tube in the horizontal position. And in part E, the magnet has exited the tube. Also note that the model says that the time in the tube was 5.874 seconds, which means that it took the magnet 5.874 seconds to fall through the tube. And this contradicts our finding in the physical experiment, where I measured the average time to be 2.002 seconds. This is a quick video of my computational model running. Now I will go over the code that made the computational model possible. The first set of code shown defines the measured length, width, and inner radius of the aluminum tube. Next, the mass of the magnet and the magnetic dipole moment are defined. And then, from Lab 3, we pull in the function to calculate the magnetic field of the bar magnet. Next is the function to calculate the time derivative of the magnetic flux through each ring. To do this, the radius of the ring must be defined, as well as the distance and the speed of the magnet. The defined numerator and denominator are used to mirror the given equation for the time derivative of the flux and adapted for use in this lab. By defining df dt to be equal to the defined numerator divided by the defined denominator, we calculate the time derivative of the flux. After this, we define the gravitational force on the magnet, which of course is the force of gravity times the mass of the magnet directed in the negative y direction. The current in the ring is then computed through this next line of code. Now we compute the typical magnetic field at each ring. To do this, we need to define the magnetic field at the ring, b hat, and sine theta. And using these, we get the magnitude of the force on the ring. The next line of code calculates the net force on the magnet, and the last bit of code updates the magnet's velocity and position as it's falling through the tube. A few questions that need to be answered. What happens to the dynamics of the system when you flip the magnet around? The speed of the magnet will be the same, but the clockwise and counterclockwise currents will be changed. How does the total time in tube of the real-world system compare to that of the computational system? And how might the computational system be made more accurate? It seems that the computational model is less accurate than the physical estimate, and I believe that the length of the tube is affecting the computational model somehow. The computational system could be more accurate by accounting for real-world conditions. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, the velocity is constant when the poles of the magnet are horizontal as it is falling, and the velocity is changing when the magnet enters the tube and when it exits the tube. Now just to answer the two what if questions. So what if the resistivity of the conductor were reduced as close as possible to zero, and how would the dynamics of the falling magnet change? The magnet would fall faster because the current would be greater. And what if holes or slots were cut into the tube, and how would this affect the ring currents in the model? There would be fewer forces acting on the magnet that oppose its motion in the negative y direction, so it would fall faster through the tube, and the ring currents would move faster down to the tube in the computational model.